Hi, I'm Antonio Sala. In this video, we'll discuss the concept of conditional independence. We'll give some definitions and common sense examples. In a second video, we'll give additional examples with a deeper relationship to control concepts. So let's start with the definition in formal terms of the concept of conditional independence. Conditional independence involves three random variables. Let's call them A, B, and C. And it discusses special relationship between B and C given A as follows. B and C are said to be conditionally independent when A is a given value. Let us call it AM, A measured, if this thing here holds. If the conditional probability of B given knowledge that A takes value AM is equal to the conditional probability of B given knowledge of A and of C. In other terms, once I know A, the knowledge of C is useless for me because it does not change my expectation, my knowledge of the probability distribution of B. I may say the same interchanging B and C as follows. The conditional probability of C, assuming I know that A takes a given value, AM, okay, that C knowing A, if it is coincident with C knowing B and A, means that once I know A, knowledge of B is not relevant in order to change my belief about C, my probability distribution. If you don't understand anything, don't worry, because in a couple of minutes we'll be putting some common sense examples. But okay, let's finish with the formal definitions of this stuff. An equivalent definition of this conditional independence is inspired in the independent variable stuff. If we didn't have A, we would say that B and C are independent if the joint probability, the probability that B is BM and C is CM, give a couple of arbitrary values, that would be equal to the products of the individual probabilities of B taking a given value and C taking the other value. In this case, B and C would be independent. What does it change in this stuff in order to define conditional independence? Well, we will put the conditioning to A, conditioning to A, conditioning to A in all those expressions, so we get what we have here. If the probability of B and C taking given values, okay, I am not putting BM, CM just to streamline notation. If the probability of given values for B and C conditioned to A is equal to the probability of set B conditioned to A times the probability of given value of C conditioned to A, well, if this product expression holds, we will say that B and C are conditionally independent when we know the fact that A has taken into value AM. For the moment being, this seems kind of playing with formulas that still do not have any interesting interpretation, so hold on and you will see it in a minute. A last refinement of these definitions. If these things hold for every possible AM in the set in which A takes values, so if this happens for all AM, then we will just say that they are conditionally independent given A. So in plain terms, this would be like, B and C seem independent when the value of A is known. The first definition meant that B and C looked independent when a given coin is heads, and the bottom definition means that, okay, they seem independent when a given coin is heads or when a given coin is tails, as long as I know the result of the coin. Well, as I said, let's give intuitive examples. Let's go. Let's first consider 3 random variables. Let's start by defining B and C, the ones we wish to understand its relationship. So B will be the power of the car engine, and C will be, let's say, the annual cost of speeding tickets the owner gets. If we don't think in anything else, we can collect data and find that B and C, the power of a car and the speeding ticket amount, are statistically dependent. The 600 horsepower Ferraris have a lot more speeding tickets than a 40 horsepower small city car. So B and C are not statistically independent, they are dependent. So we need to look further to try to address the nature of that dependence. Then someone hints us that maybe speed when ticketed has some role in the explanation of this statistical relation between B and C. Aha. Is it true? Well, let's think. The important concept we realize is that if you are running at 200 kilometers per hour, the fine you get is the same independently of the power of your car. I stress independently because this is the intuitive interpretation of the above formulas, okay? Once I know the speed when I got the fine, the amount of the fine is independent of the power of my car. So B and C appear to be correlated. I mean, they have correlation, but the correlation is kind of a consequence of the values of A. We can draw kind of a diagram in which we have A, speed when ticketed. So speed when ticketed is the only thing that influences the actual cost of my fines, and A is a sort of intermediate variable which depends on power. Yes, I mean, if my car is more powerful, then I will be likely to drive at higher speeds. I mean, I will not drive 200 kilometers per hour with a 40 horsepower vehicle. So with this diagram, we understand that if I know A, then I can sort of split my reasoning about the statistical relationship between power and cost of my speeding tickets. I can split it into independent, I mean formally into conditionally independent phenomena. The first phenomenon is that high power makes me likely to drive at a higher speed, so power and A are correlated. And the second phenomenon is that higher speed makes me pay higher fines, so power and cost are statistically dependent because of the intermediate variable A, but if I know A, I can split that statistical relation into conditionally independent statistical computations. Well, this is the meaning in common sense of that conditional independence, kind of the ability to find intermediate variables between two correlated variables, explaining that correlation in a kind of multi-step conditionally independent explanation. So this kind of diagram will be later called Bayesian network, and the lack of an arrow between power and cost will indicate that they are conditionally independent given A, this kind of conceptual splitting of the statistical correlation between B and C. Let us now see second example. My second example will be 2 rolls of dice. And it's important getting the concept that statistically independence does not say anything about conditional independence. In the car example, B and C were dependent but conditionally independent. And now we'll see the reverse. Independent, but not conditionally independent. Okay, let's delve in. If I think in 2 dice rolls, then I get a random number between 1 and 6. And of course, usual assumption is that the second roll of the dice will be statistically independent to the first one. So I get 2 statistically independent numbers between 1 and 6. That will be random variable B, first try, and random variable C, second try, second roll. Every one of you understands that they are statistically independent. However, let us imagine that God gives us an additional piece of information. Someone tells to us that you didn't see the actual dice, but I can tell you that their sum was 11. Well, that thing will be the variable A. If their sum is 11, then things change a lot. I have either 6, 5 or 5, 6. I have only 2 possible values, and also the relationship between B and C becomes deterministic, which is exactly the opposite of independence. If I know that the first one was 5, then the second is 6. Or if the first one was 6, the second is 5, period. No other choice. So when I know variable A, their sum, then 2 things that were clearly statistically independent before knowing A, now knowledge of A, makes their relationship completely deterministic. If I know one, I know the other. So this means that the variables are now conditionally dependent, given A. I mean, they cannot be more dependent than deterministic. It's the total dependence, no randomness remaining when I knew one of them. Let us now discuss a last example. This is similar to the car. In the car we had 2 dependent variables. There was correlation between power and speed in tickets, but they were conditionally independent with some extra piece of information. Then this is another case of the same phenomenon. Let's go on with this example. We will have a random variable B, which will be the height of a given randomly chosen person. And the variable C will be having a college degree. Went to university and they got a degree in medicine, law, or engineering. Well, if I choose a random person and I gather data of a lot of people, then we can readily see that taller people have more university, college degrees than short people. Wow, this seems kind of surprising. Well, it's not. You know, babies and 3-year-old children do not usually measure 2 meters. So as we are including children and babies in the group of randomly chosen persons, then for sure the likelihood of a university degree between the shortest segment of the population will be almost 0, but the likelihood of a university degree between people that measures more than 1 meter 70 centimeters will be, let's say, 30%. So height and college education are indeed statistically dependent. There is a positive correlation between height and educational level. But let's explain that correlation, splitting it into this conditionally independent stuff. The intermediate variable that explains everything is age. You know, if I choose for my sample only people above 26 years old of age, then there is no remaining correlation between height and college degree. Tall people which are over 30 have the same likelihood of being a lawyer than short people. as long as those short people are also chosen between the segment of the population that is over 30. So I found a Bayesian network explanation in which age influence height and the level of education that people achieved. So the positive correlation between height and education was caused by the simultaneously positive correlation between age and height and age and education. But once I conditioned to age, there was no remaining correlation between height and education. If I randomly sample people of a certain age, then I see no remaining correlation. So again, conditional independence allowed me to explain the statistical relationship between B and C via an intermediate variable A, so that knowledge of A allowed me to split the explanation into two conditionally independent sub-explanations. Well, this is it, so let us conclude. In this video, we have introduced the concept of conditional independence. We have introduced it sort of, first formally with some expressions on the product of conditional distributions or on the value of further information given A. So actual computations in computer code using Bayesian networks will use this fact to propagate belief in this kind of networks. Of course, details are not in the scope of this material, but the important thing in this video were the examples to intuitively understand what we were talking about, which is that conditional independence allowed us to explain the relationship between two statistical variables, B and C, given an intermediate variable A, by splitting the knowledge into conditionally independent things. Relationship between power and speed tickets in a car can be explained by a diagram like this. Power influences speed, speed influences tickets. I can split like here. The rolls of dice can be explained like this. They go on their own, but okay, they both influence the sum. So knowing A changes my belief on the relationship between B and C. They are no longer independent. And last, we have a diagram like this where age, A, influences height and education, explaining the positive correlation between them. Good. So we'll finish with this. And as I said, in a second video, we will discuss control-related examples of the idea of conditional independence. Thanks for watching. Bye.